All right, welcome back, everyone. Today we are starting chapter 6, which is about spatiotemporal determination of the traffic state. And we are going to only cover the first section of this chapter, which is spatiotemporal interpolation. And in this section, the chapter has covered the method of isotropic smoothing. And let's see what the goal of doing isotropic smoothing is. So we have looked at this figure before, which is about detector data. And on x-axis, we have time. On y-axis, we have the detector position in kilometers. And we can see for each detector the time series of the macroscopic speed. The speed is also colored. And we can see the stop and go waves. Let me switch my screen so that I can show you a uh, version of the figure which is zoomed in. So this is that same figure, and let me know if you don't see it. This is the same figure which is zoomed in, and I'm highlighting here one stop and go wave. So we are looking at the time in point of 8:20, and at this point we see that the speed color here is red, so it's almost stopped. It's very small speed, and then between this detector, which is coming from the detector number 473, we have another detector, which is detector number 474, where we have the time series of macroscopic speed. At the exact same time, the speed there is what we call as go. So this is stop and this is go. So this constitutes one wave of the stop and go waves. And so this happens in cycles at this point in time. We can see again there is go, the speed is higher, or actually it is closer to stop. It's actually in between. So it's not exactly stop and it's not exactly at a higher speed, but it's in the middle. And then here it's the higher speed. So we see this is happening in cycles, stop and go, stop and go. And so just to remind you what's happening here is that we are moving from the bottom of the figure to the top. That's the direction of motion. And the downstream is where there is an intersection, as we discussed in the previous chapters. At some point, vehicles change lanes and they have to stop. So that is the traffic jam that is generated downstream. And that traffic jam is then propagating upstream towards the bottom of the figure. And that's what is happening here. These black lines represent how those traffic jams are traveling in time. So when there is a decrease in speed here, that decrease in speed is then seen here later in time upstream of this figure. So this constitutes one wave of go and stop. And if we consider up to this point, that will be the second stop and go wave. So considering these definitions of the stop and go waves, we now go back to our chapter and look at what is the purpose of doing spatiotemporal interpolation. The purpose is to study the historical traffic flow, to understand the pattern in the traffic flow in a certain region. And so we go from this figure, the first part of figure 6.1, to this second part of the same figure, where we again have time on x-axis and location on y-axis, but we now see a complete continuous surface of the speed rather than discrete speeds. This is also called as speed field, which is defined here. Speed field that is a continuous function of local speed average v of xt given only discrete speed measurements. Small vi is equal to v of xi di at discrete locations xi and times di. So the discrete locations are these detectors, and the times di's are when the speeds are uh, reported to us by the detectors at time ti, for example, at time 8 a.m., at 8:20 a.m., and so on, and is generally considered or reported after every 60 seconds, as we discussed in the previous chapters. One point about terminology here. In the previous chapters, the same authors have used this small vi to represent single vehicle data. The small vi previously represented one vehicle i's data. In this case, I represents the reported speed or reported variables at at different intervals. So I here represents, for example, for detector one, what is the location x and what is the time at which the speed was reported. And as we know, speed is reported after every 60 seconds and at every detector. So those are discrete speed measurements. And what we want is a complete speed field, which is a continuous surface that looks like this. So how do we get to this point? How do we create this continuous surface? One way to achieve that is using this equation, which is mathematically a discrete convolution. But even if you don't know what convolution is, we need to figure out what these parts of the equation represent. So as we discussed, VI is the macroscopic speed measurement at discrete at xi, which is the location of the detector, and time ti. So once we get that speed, we multiply it with this thing, which is called as a kernel. And so we multiply it with a kernel, which is essentially weighting this speed. So how do we appropriately weight the speed? What should be the function of this kernel, phi naught? So for that, we have these requirements. One requirement is that it should be localized, which means that if we are closer to a detector, then we give it more weightage because that is where we are getting the ground truth about the speeds, right? But what we don't know is what is happening between two detectors. That is what we are interested in. So this phi naught function should be localized. It should tend to zero for sufficiently large values of x and t absolute values. So x here again is the location where we are interested to get the speed value, where we don't already have that speed value. We only have the speed value at xi, which is the location I, or given by the detector. Similarly, we only know about the speed value at time t given by the detector, but we are interested in at time t, which could be any time between when the speeds were reported. So we are looking at the difference between the location we are interested in compared to detector's location and the time we are interested in compared to when the speed was reported. So we want to see what is the speed on other locations and other times other than what is given by the discrete measurements. We also want the weightage kernel to have a maximum of this thing. So it would be 1 when x is 0 and t is equal to 0, which means that when you are exactly at the detector and exactly looking at the time when the speed was reported, the weightage is the highest, right? We are giving full weightage to that because that is ground truth. As we go away from the detectors and other times when the speeds were reported, for those, obviously the weightage will be smaller. Similarly, that weightage factor should be continuous function of x and t, and it should also be monotonically decreasing with the absolute values of x and t. So as we have larger values x and t, phi naught should move towards 0, which is also this point. So let's see one example of what that function could look like, which is given in equation 6.2. We are comparing again the location we are interested in with the detector location, the time we are interested in with that time reported when the speed was reported, and we are dividing them each with smoothing factors, sigma in space and tau in time. And then once we get this evaluation of this expression, we then make it negative, and then we take an exponential, which means that the higher this value is in absolute terms, the smaller the result of the exponential would be, which means as we go farther away from the detectors, from the ground truths, you are essentially getting zero values or very small values because you're not weighing closer to the actual values. So our goal is to go from, again, discrete measurements to continuous surface like this. And in that same equation, the n is the summation of all these weightage measurements. Again, look at this figure, sorry, this equation where we have the actual speeds coming from the detectors, and then we multiply it with the weightage factor or the kernel and divide it by n. So sigma and tau, as I said, are the smoothing widths in the spatial and the temporal coordinates. Now, this is important that this exponential function that we saw in the previous equation is also called as a low pass filter, and it's because it is going to smooth the temporal variations on a scale smaller than tau. If we have a small value of tau here, let's take an example. Let's say that we know exactly what is the speed at 8:20 a.m. and we want to know what is going to be the speed after only 20 seconds. In this example, the aggregation interval of the detectors is 60 seconds. So we don't know what is going to happen after 20 seconds. What we'll only get from detectors is after 60 seconds from 8:20, so at 8:21. But we want to know what is happening at 8:20 and 20 seconds. So 20 seconds after this time. So for this purpose, when we take t, which is 8:20:21, minus ti, which is 8:20, the difference is 20 seconds. For this example, let's take an example of tau. Let's say it is 30 seconds. So if we increase or decrease the value of tau, that will make a difference to the evaluation here. The exponential will be smaller if the tau is higher. If the tau is smaller, then the exponential will be smaller as well. And so whatever is the result of a higher tau, if we apply a higher tau value, the exponential will give us a smaller value inside this expression, and the result of the exponential, sorry, would be a, smaller value. Actually, the smaller this value is going to be, the larger the exponential would be. And we can just try that right here. If we have the exponential of, let's say, minus 0.1, we know that the value is going to be 0.9. If I change it to 1, it decreases the value. So the higher the evaluated value inside this expression is, the smaller the exponential is, which means that this is only going to be higher when either these differences are higher or tau and sigma are higher. For now, let's ignore this part, only consider the time part, and only consider the value of the tau. T minus Ti is fixed to 20 seconds. If we increase tau to, let's say, 60 seconds, this result will be small and the exponential will be large. So you're giving more weightage. But if tau is decreased from 60 to 30, this result is going to be larger and the exponential will be smaller. So you're giving smaller weightage. So this changes based on what value of tau we are going to use. So what they recommend here in the chapter is, they say for the interpolation of detector data with aggregation intervals of 1 minute, good values of tau are between 30 and 60 seconds. So any value smaller than tau will be smoothed away. Any value larger than that will not be. The spatial smoothing with sigma, this is for obviously in space, should be of the order of half of the average distance between detectors. So if the distance between detectors is higher, then obviously what is happening in the middle in terms of speed, estimated speed value, is going to be affected by how far you are from the detectors. If you are closer to detector, that detector's value is going to dominate. And that's what happens with this equation, isotropic kernel. It creates what is called as egg carton pattern, because if the distance between two detectors is larger than half of the spatial distance between two stop and go waves, the isotropic kernel produces artifacts such as the egg carton pattern. So in our example, we have this as one stop and go wave, and then up to this point will be another stop and go wave. So these are two stop and go waves. If the distance between two detectors is larger than this, then isotropic kernel would create this thing, this result, the right part of figure 6.3. And that is because it is focusing more on or weighting more the values of speed on individual detectors. It does not know that the traffic jam moves upstream like this in a diagonal pattern. And so it is going to focus more on the values closer to the detectors. At exactly the detectors, it's going to give the highest weight, sigma, sorry, not sigma, phi naught, and it's going to create these patches or egg carton shaped uh, blotches on this speed plot. So that's the limitation of the isotropic kernel if the distance between two detectors is larger than half of the spatial distance between two stop and go waves. In this case, that's not the case because we have detectors in between them as well. If there was only one detector here and one detector here, then this would produce that Eckarton problem in the chapter. So later in this chapter, they discuss the adaptive smoothing method, and this is where they will use a different methodology to address this problem of Eckarton issue. And this is going to give us a better result as we see here, which is representative of the actual issue of moving the jam upstream, but in a diagonal fashion because it happens at different point in time in different detectors. So this is the result of adaptive smoothing method, which will be our next discussion point in the upcoming chapters. So any questions? All right, I guess there are no questions. So we stop here. I know that this is a very small discussion, but this is pretty complicated in my opinion. So I'll try to also make a small example of some data and then show you step by step in the next week how the Eckart problem is generated. So see you in the next session. Thank you.